Okay, so I'm going to continue on with this chapter 10, radical reactions. So in the first part of this, in 10a, we talked about kind of like the basics behind radicals. So we talked about radical stability. We talked about kind of various patterns with respect to drawing resonance structures for radicals. We talked about mechanisms, right? And specifically, we started talking about at the end a specific mechanism or a specific reaction that we also detailed the mechanism for, right? So the first reaction that we talked about with respect to these radical reactions was the chlorination of methane, right? So in this reaction, we had methane, so CH4. We reacted it with chlorine in the presence of light because, again, we need that energy to undergo this radical reaction. And the product that we got here, if we controlled it correctly, was monochlorinated methane or methyl chloride, right? And then we also got HCl as another product, okay? All right, so this is what we started with. We talked about how with respect to all of these radical reactions, they all have an initiation step, they all have a propagation step, and they all have a termination step, okay? So now the question is, that we have been left with is, okay, so this can occur for chlorine, right? This chlorination of methane. What about fluorine, bromine, and then iodine, right? That was a typo. So what about fluorine, bromine, or the other halogen that we frequently talk about, iodine, okay? And so do these reactions occur is essentially what we're asking, okay? So again, if we want to predict whether or not something occurs, we go back to Gibbs free energy. If we have a delta G that is negative, that tells us that we do get a spontaneous reaction, a spontaneous process, whereas if our delta G is instead positive, that would tell us something about the reaction being non-spontaneous, that it would not occur with any outside intervention, okay? And remember that delta G consists of two different terms, right? We have the enthalpy term, we also have the entropy term, okay? Now, the question is, okay, does this reaction occur for fluorine? Does it occur with bromine? Does it occur with iodine? Regardless of the halogen we're using, we can kind of use this guy as our overall general equation for this reaction, right? So we have methane, we're reacting it with a halogen. This can be any of them. We're producing our halogenated methane product as well as H halogen, so HX, okay? So because we're going to utilize this as our general overall reaction, we can kind of get an estimate here for delta S. So remember, delta S was this measure of disorder in a reaction, or a better way to understand that is like a measure of randomness of motion or degrees of freedom, right? So how much motion do these molecules have? Are we increasing that or are we decreasing that in our overall general reaction? And so we can kind of estimate that by just looking at the number of molecules that are involved in our reactants as well as the number of molecules that are involved in our product, okay? So we find that for all of these halogenation reactions for methane, we have 2 molecules as our reactants and we're making 2 molecules as our product, right? So we don't increase the number of freely moving molecules, we also don't decrease it. So we can kind of use this to estimate that delta S for these reactions is approximately going to be 0, right? We're not really increasing freedom of motion, we're not decreasing it either, okay? So with that, if delta S for all of these reactions is 0, then delta G, right, which is going to tell us about the spontaneity of this process, can kind of just be estimated from the enthalpy of reaction, from the heat of reaction, okay? And again, we talked about how we can either calculate delta H or estimate delta H given bond energies, right? So in chapter 6, we dealt with calculating delta H from bond energies. And the way we did that, if you go back, is we took the sum of the bonds broken in a reaction, and we subtract from that the sum of the bonds formed. And again, these bond energies would have to be given to you. You'd have to look at the bonds that you're breaking, look at the bonds you're forming, and then estimate delta H from that, okay? I'm not going to actually have you guys calculate that, but instead I'm just going to give you the overall values, okay? So delta H depends on, again, the halogen that we're using in this reaction, right? So if the halogen is fluorine, we find that the enthalpy for this reaction ends up being very large and negative. So this ends up being 431 kilojoules per mole. If the halogen is chlorine, it's still negative, so it's still exothermic, but it's not as negative. So I think this ends up being minus 100 kilojoules per mole, if I remember correctly. 104, 103, pardon me. For bromine, it is still exothermic, right? So this ends up being much less so it's 33 kilojoules per mole. And then for iodine, we move away from the exothermic nature of this and instead have an endothermic reaction of a positive 55 kilojoules per mole, okay? All right, so again, enthalpies for these reactions are going to tell us about delta G for this reaction because the entropy is approximately 0, okay? So if we have an exothermic reaction, which is what we do for fluorine, what we do for chlorine, what we do for bromine, these guys are all going to also be exergonic. So these guys are all going to be spontaneous, okay? Now, the one that isn't spontaneous here is iodine. So iodine is a positive value. This is an endothermic reaction. So that's going to allow us to essentially say that, no, this reaction is not spontaneous. So this reaction is not going to occur. So we're not going to consider the iodination, the radical iodination of methane because it's not a spontaneous reaction, okay? Okay, so with that, we can rule out iodine because it's endothermic, right? We can also rule out another one, which ends up being fluorine, okay? So fluorine, even though it is spontaneous, is too spontaneous, right? This is too exothermic, and because it's so exothermic, it tends to react violently. And because of that, it's not practical for any type of actual experimental uses, okay? So this guy, even though it's, it is exothermic, it is spontaneous, it's too spontaneous, and we can't actually utilize it for any type of synthetic purposes, okay? So because of that, we can cross out fluorine. We're not going to be able to use that either. That leaves us, for our halogenation of methane reactions, that leaves us chlorine as a potential halogen as well as bromine. Okay, so we're going to consider these two only moving forward. Okay, so we again had started with this radical halogenation of methane, right? And we'll find that for both bromine and chlorine, that halogenation of methane is spontaneous and it will occur. And bromine is going to occur and react in the exact same way that chlorine will if we went ahead and detailed out the mechanism. I'm not going to do that for methane, but we are going to do that for other ones. So just hold off on that, okay? So now we're going to move forward, only considering bromine and chlorine. And we're going to move forward to, let's say, instead of methane, let's say ethane, right? So let's say that we had ethane as our alkane, and we want to radically halogenate it as well, right? So we're taking our ethane, we're reacting it with either bromine or chlorine. Again, that's what X is representing in the presence of light. And the question is, what do we get? Do we get our halogenated product, right? So do we actually get this reaction with ethane as opposed to methane? And the answer to that is yes. Okay, so this does occur where X is either bromine or chlorine. Both of these guys are spontaneous. Okay, so we'll find that for chlorine, the overall reaction is about minus 117 kilojoules per mole, whereas for bromine, it's about minus 50. Again, both of these are exothermic, so they both will occur. And the propagation, which again is going to kind of detail the overall mechanism for these radical reactions, the propagation step is exactly the same as we saw for methane, right? So the first step in this, we get a hydrogen abstraction step. So again, X is either bromine or chlorine here. So in that hydrogen abstraction, we're going to have our halogen come in as our radical. Again, this was created in that initiation step. It's going to abstract a hydrogen, right, which is going to create our ethyl radical, okay? That ethyl radical is then going to go and attack and abstract a halogen. right? So we're going to get a second step where we produce our halogenated product, right? And we produce our halogen radical, which is then going to go back in and essentially restart the reaction in that chain reaction format that we talked about before, okay? So both of these steps are the same, right? Whether or not we're using chlorine or bromine, okay? Now, there's something important to note here, okay? So again, both of these are exothermic, regardless of if we're using chlorine or bromine, but there is a little bit of difference in the two different steps, right? So that first step, that hydrogen abstraction step, that is an exothermic step if we're using chlorine, right? So we get a negative value here. Whereas this first step, if we're using bromine, is actually endothermic overall, right? So this guy is endo, whereas this guy is exo, okay? If we drew out the energy diagram for both of these, so if we went ahead and drew out our energy diagram, so just as a reminder on the bottom here, this tends to be something like reaction progress. Over here, we'll say this is energy, delta H. So for the overall two steps for chlorine, both of them are exothermic, right? So we're going to have our reactants at a high energy state. They're going to react in an exothermic process here. And again, we're measuring this guy via, let me draw this a little bit better. So exothermic, we're measuring the exothermicity between the difference in energy between our reactants and our intermediate, right? And then that second step is also exothermic. And again, we're measuring that exothermicity, or that delta H, be the difference between this intermediate and our products. Okay, so this would be step number 1 for our chlorination reaction. This would be step number 2 for our chlorination reaction. Okay, again, both of these guys are endothermic, and it's, an exothermic, and it's an exothermic process overall. Now, bromine is going to look a little bit different, right? So for bromine, if we did the exact same thing down here, because that first step, delta H, delta H, and let's write out reaction progress. Because that first step is endothermic, its reaction coordinate diagram is going to look slightly different, right? I'm going to go ahead and draw that in red. So for bromine, we're going to start here as our reactants. This first step, because it's endothermic, we're going to see a large increase in energy, and that intermediate is again going to be at a higher energy state than our overall reactants, because again, this process right now is endothermic, okay? So that's our step number 1, that's our hydrogen abstraction. Then we're going to go in, and that second step is going to be exothermic. Again, this is the difference between our intermediate and our product. And again, the overall reaction, the difference between our reactants and our products is also exothermic, okay? Okay, so now because of this, right, if we looked at the difference in the activation energy for this first step, right, what we're going to find is that for our bromine, which is what we're detailing down here, because that activation energy in that first step is so large, because that first step is an endothermic process, this is much slower of a reaction. Let me go ahead and write that correctly. This is much slower kinetically comparatively to chlorine, which is much faster because both of those steps are exothermic, right? So the activation energy here comparatively is much smaller compared to the activation energy for bromine. And because of that, bromination is a slower process compared to chlorination, okay? Okay, so those are not the best energy diagrams, but you kind of get what I mean, hopefully. And you can look at the book. They make much nicer energy diagrams as well. Okay, so again, the question here was, okay, we're looking at bromine, we're looking at chlorine. Do we see the same thing with respect to ethane as we saw for methane? The answer is yes, right? So we're going to see the same propagation mechanism where we have a hydrogen abstraction and a halogen abstraction. The difference between chlorine and bromine comes in that first step. That first step for bromine is endothermic, whereas for chlorine it's exothermic. So because of that, chlorination is much faster of a reactant compared to bromination due to the fact of the energy differences in that first step, okay? Now, I know this kind of seems silly. Why are we going over this? But it's actually going to be important long term even though bromine is a slower reaction, it's going to allow us essentially the ability to control the outcome of the products a little bit more. And so that's why we're kind of talking about it now. We're explaining why we actually see the product distribution that we do by going back to the fact that these reaction mechanisms are slightly different between chlorine and bromine. Okay, so we've kind of discussed the different reactions for methane, and we just talked about the halogenation reaction for ethane. We know now that we're essentially only considering halogenations of chlorine or bromine, so the radical chlorination or the radical bromination. We've factored out fluorine as well as iodine, okay? Okay, so with respect to methane, right, so we had methane, we talked about chlorination of methane, also talked about bromination of methane. We also have now talked about ethane as well, right? So for both of these radical halogenation reactions, regardless of the hydrogen that was abstracted, we were always going to get the same product, right? So for example, as long as we controlled the amount of the halogen that we added, as long as we had a large excess of our alkane, we were always going to get just the mono halogenated product, right? So for methane, that was, let's just say, the methyl chloride. For ethane, regardless of the proton that we took, we were always going to get the exact same product, which was just going to be our halogenated or our chlorinated ethanes, or our ethyl chloride, right? Now, when we move up, so we talked about methane, we've talked about ethane, the next alkane that we'll move to is propane, right? So propane, if we take propane, and again, we undergo this radical, let's start with chlorination, what we're going to find is actually we have two different hydrogens that can be abstracted, right? So we have two on this interior carbon, but then we have the potential of 6 different hydrogens on this let's say terminal carbon that would give us the same product. Okay, so if we had our radical chlorine come in and it had abstracted, let's say, this hydrogen, then the product of that would have been this secondary alkyl halide, right, where the chlorine would end up on the interior carbon, right? If instead the chlorine radical had come in and abstracted any of these guys on the outside, then that would have given us our primary alkyl halide over here, our primary alkyl chloride, okay? So with ethane, with methane, we didn't have to deal with that because regardless of the hydrogen that was abstracted, we're always going to get the same product overall, right? But now there is a difference depending on which proton is abstracted. If we abstract from the interior, we're going to get a secondary alkyl halide. If we abstract from the exterior hydrogens, we're going to get a primary alkyl halide, okay? So now, if the product distribution between secondary and primary only depended on the probability of hydrogen abstraction, then we would expect to see the following distribution, right? So we know that we only have 2 hydrogens on the interior that would give us this secondary alkyl halide, whereas there are 6 hydrogens on the exterior that would give us this primary alkyl halide, right? So if this was probabilistic, right, then we would expect, well, 2 out of the 8 total hydrogens would give us about 25% as a prediction for our secondary alkyl halide, whereas 6 out of the 8 total hydrogens, that would give us about a prediction of 75% of this guy, right? So if this distribution between secondary and primary was just based on probabilities, then 25% of the time we would expect to find this guy, and 75% of the time we would expect to find this guy, right? And so we can actually go in, we can do this reaction, and we can see the product distribution for real. And what we find instead is not this 25-75. Instead, we find a 60% product distribution for our secondary alkyl halide, and we find 40% of the time it's going to be this primary, right? So essentially, this kind of turns our prediction on its head, right? Where we had predicted the secondary to be less, it's actually more, and we had predicted the primary to be much greater, and it's much, much less than what we really predicted, okay? So now the question is, well, why? Why do we see 60% of the time it forming this secondary and only 40% of the time it forming this primary? And the answer to that goes back to, again, this idea behind transition states and the reaction intermediate that we form, right? So in this first reaction, or in this first step of this reaction, we do that hydrogen abstraction, right? So if we have our propane and we have our hydrogen in the interior, and we have our chlorine come in, again, we're going to see that first step be hydrogen abstraction. And so the product of that overall is going to be a secondary radical. Whereas if instead we had that exterior hydrogen be abstracted in that first step, then the product of that overall would have given us a primary radical, right? So with respect, this again is going to be the intermediate species, right? So with respect to that, we know that the secondary radical is more stable. And we also know that the transition state, right, or the structure of the transition state for both of these are going to have some sort of partial radical character, right? So both of these guys are going to have some sort of partial radical character because, again, the intermediate species is that full radical, okay? So because this transition state does have this partial radical character, the more stable we can make that partial radical, the better, or the lower the energy of the transition state we're going to find, right? So because secondary radicals are more stable than primary radicals, the transition state energy for that formation of the secondary radical is going to be lower compared to the transition state of the primary radical. And because of that, that activation energy is also going to be lower, right? So the activation energy in forming this secondary radical is going to be lower than the activation energy of forming that primary radical. And since the activation energy is lower, then the rate of the reaction is much greater. So rate increases because the activation energy decreases here. So for chlorination, and I know I just keep flooding into more words, for chlorination, we do have the formation of a partial radical character in the transition state. The more stable we can make that radical, or that partial radical in the transition state, the lower its energy is going to be, and therefore the lower the activation energy for that reaction. So the reason why we see a greater formation of the secondary alkyl halide is because the energy of that transition state is lower, the activation energy is lower, so this reaction occurs at a faster rate comparatively to the formation of the primary. This is going to be a little bit slower because its activation energy is going to be a little bit larger, higher. Again, though, regardless, it's faster, but it's not like so much faster that you don't see formation of this primary alkyl halide, okay? Okay, so again, we're going to get both with chlorination. We are going to see a little bit larger of a preference for the more substituted alkyl halide because the activation energy is lower for that. All right, so now that's chlorination, right? So now we're going to talk about bromination. And again, if you're thinking about this and you're saying, well, you know, in a reaction, we don't want a mixture of products usually. Really, we want just one product. That would be the best. This 60-40 mixture is not going to be what necessarily we're going to want long term, okay? Now, if we talk about bromination of propane, right? Take propane again, and instead of chlorinating it, we're going to react it with bromine. Again, we're going to get overall an exothermic reaction. But now the product distribution is pretty different, right? So for chlorination, we saw 60-40 between the secondary alkyl halide and the primary alkyl halide. For bromination, though, we see a 97% formation of our secondary alkyl halide and only 3% formation of our primary alkyl halide, right? So the bromination reaction is much more selective for the more substituted alkyl halide, okay? And again, we can go back to this idea behind these energy diagrams and this pathway, this mechanistic pathway, to help explain that, right? So remember, with respect to chlorination, that first step in taking the reactants to that radical intermediate was an exothermic process, right? So we had an exothermic process. We just explained the kind of preferential formation of the secondary alkyl halide here in terms of the fact that we do get a partial radical character here. But if we go back to this idea behind the Hammond postulate, remember the Hammond postulate stated that the closer 2 points are on an energy diagram, the closer they are in structure, the more they resemble themselves in structure. So because this is an exothermic reaction, the structure of the transition state, if you guys remember exothermic, the structure of the transition state resembles the reactants more than the products. So we have resembles, I guess so, reactants more than, so transition state structure resembles reactants more than products. Because again, the energy of the transition state is much, much closer to the reactants comparatively to the products. And the products in this overall first step is that radical intermediate, okay? Now, with respect to endothermic reactions, which is what we see in step 1 of the propagation for bromination, that was an endothermic process, right? And so for endothermic reactants or reactions, we found using the Hammond postulate that the transition state actually more closely resembles the products, right? Because again, if we go back to an endothermic reaction, the energy level of the products is much closer to the energy level of the transition state, okay? So again, the product in this step 1 is not the overall product from the reaction. It's instead that formation of that radical intermediate species. And so because this is an endothermic process and the transition state resembles that radical intermediate more than what we found for this exothermic chlorination reaction, bromination is essentially going to be much more susceptible to this stabilizing effect from the radical, right? There's going to be a much larger partial radical formation in the transition state. And so because of that, the more stable this radical species is, it's going to affect the energy of this transition state much, much more than what we found for our chlorination reaction instead, right? For chlorination, because it was exothermic, it did help stabilize that transition state, but the overall effect is going to be much less than what we see in our bromination reaction because it's endothermic, okay? So again, for endothermic reactions, for this bromination reaction, because it's much more susceptible to the stability of the intermediate radical that's formed, we're going to see a greater lowering of the activation energy dependent on the type of radical that we're going to form. So tertiary radicals are going to really dramatically lower the activation energy of that transition state comparatively to primary radicals or secondary radicals. So because of that, these guys are going to be much, 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 much faster than primary or secondary, and we're going to see essentially complete formation of the more stable radical or the more substituted alkyl halide. So complete formation. So for example, if we took let's say 2-methyl propane, and again we had to undergo this bromination reaction. So we have bromine, this radical bromination in the presence of light. We have 2 potential products that we could get, right? We have a hydrogen that's ready to be abstracted here, and we also have this exterior hydrogen that's ready to be abstracted, right? So dependent on the hydrogen that we take, we're either going to get a tertiary alkyl halide, or we're going to get a primary alkyl halide with the bromine going to this exterior hydrogen, abstracting this exterior hydrogen, right? So we have 2 potential outcomes here, right? Because bromine or this bromination is much more selective, we actually don't get any formation of this primary alkyl halide. We get essentially 100% formation of this tertiary alkyl halide, because these energy differences up here are so large because that first step is endothermic. So I know I probably really didn't explain that the best, but long story short, right, chlorination, even though that first step is exothermic and it's a faster overall reaction, does not give us as great of selectivity with respect to our products, right? So bromination is slower because it does have an endothermic first step, but because it's slower and long-term less reactive, it actually gives us more selectivity in our product distribution. Selectivity in our product distribution. So bromination will essentially 100% of the time select for the more stable radical or the more substituted alkyl halide, whereas chlorination will not, okay? And this is going to be kind of an overarching theme that we're going to find in a lot of our reactions, is the overall less reactive the reaction, the more selectivity we actually gain in being able to control the products that we actually get out of it, the product distribution, okay? So, again, I think I meant bromination up here. Long story short, the reaction that we're really going to move forward with is the bromination reaction, the radical bromination, because it does allow us to control the products, right? So we know that we'll get almost 100% of the time the more substituted alkyl halide. And moving forward, that's what we're really going to use, okay? Okay, so let's go ahead and try a problem. So I have a product, or I have a reactant here. I have an alkane molecule, and I want to know what the product of this radical bromination reaction is. And again, I know this is radical bromination because specifically it's Br2, and more specifically, it's in the presence of H-nu. So this again was light, if you guys remember. Also, I know this is going to undergo radical bromination because I have an alkane here with no other functional groups as a part of it. So this is an alkane with no functional groups, okay? Okay, so the question is, well, what is going to be our product, right? So major product obtained following radical bromination. So the question is going to be answered in the fact, well, what type of alkyl halides could we produce, right? So, for example, if I took off a hydrogen from this guy, right? Actually, let me go back. I want to copy paste this because I'm lazy and I don't want to redraw. Right, so if I took off, let me just do that a couple times. Oops, no, I don't want that. Same thing, let me copy paste, let me copy paste, and one more. Okay, so if I went in and I said, okay, I'm going to react, or I'm going to abstract a hydrogen from this one of these terminal alkyl groups, the product overall that we would get would be something out here, which would be a primary alkyl halide. And again, this would have come after that first step from the formation of a primary radical, right, which is not super stable, okay? If we pulled something from out here, we'd get the exact same thing, right? But instead, it would be on the other one, which would be, again, because that bond can rotate, the exact same thing. We get a primary radical formation, and then in the halogenation step, we would get that bromine attaching there, right? So for both this hydrogen extracted and this hydrogen extracted, we're going to get the formation of a primary radical and a primary alkyl halide, okay? Now, if we had gone in and instead abstracted, let's say, this hydrogen, right, that would have given us a radical forming here, which is a nice tertiary radical. And then long term, that tertiary radical, after the halogen abstraction step, would have given us our tertiary alkyl halide, okay? We have other options here. So if we went in here, we have two hydrogens here that can be abstracted. That would have given us the formation of, again, a secondary radical. And again, after the second step in this mechanism, that secondary radical would have turned into a secondary alkyl halide. And then finally, I'll go off in green, there are no protons here, or no, I shouldn't say protons, that is wrong. There are no hydrogens here to be abstracted. And then finally, we have these guys on the outside, which have a bunch of hydrogens that can be abstracted. But again, if we did that for any of those, we would get the formation over here of a primary radical again. And then after the halogen abstraction step, that would have given us a primary alkyl halide. Okay, so again, this bromination reaction is extremely selective for the formation of the most stable radical. So it's always going to react at that hydrogen that's going to give it the most stable radical. The most stable radical is the tertiary radical, right? So because of that, you would predict this to essentially 100% form this product. So this would be our major product. And you would not predict the formation of any of these other guys because they're less stable overall comparatively to the tertiary radical. So question is, hey, what does the major product obtain upon bromination? Your answer here would be this guy, which is very similar essentially to determining the weakest bond that we did before. Again, you're looking for who's actually going to form that most stable radical. The tertiary radical is the most stable radical in this example. Okay, so that's that. Just as a note too, this again, I'm trying to get across the point. The chlorination reaction, if we had instead used chlorine here, we couldn't necessarily, we would be able to say that this would be the major product, but again, for this reaction, it will be 100% this guy forming, this tertiary alkyl halide. For something like chlorination, maybe it would have been like 60% or 50% this tertiary, and that's why we use bromination as opposed to chlorination, because we can 100% of the time get the more substituted alkyl halide as our product. Okay, so go ahead and try this one on your own. I want to know what the major product is upon taking this alkane, this cyclic alkane, and undergoing this radical bromination reaction. So go ahead, give this a shot, pause the video, and then come back for the answer. Okay, so we'll go over this one. So we're looking for the major product upon radical bromination with this alkane. So again, we're looking for the various types of products that can form by abstracting different hydrogens. So if we started up here with this hydrogen, we would get first off the formation of a primary radical. My radicals and my degree sign look the same, which is frustrating, so I apologize for that. So we would get the primary radical here, and again, after the halogenation step, that would turn into a primary alkyl halide. If we instead had taken from one of these interior hydrogens, so all of these guys have two hydrogens to abstract, we would again get the formation of a secondary alkyl halide, or a secondary radical, which is more stable than primary. If we had taken from this guy, there is one proton here that can be abstracted. That would have given us the formation of a tertiary radical, which is more stable than secondary or primary. If we had moved down here, there's no hydrogen. And then if we had taken any of these guys, so we have a hydrogen here, that would have also given us the formation of a primary radical, right? So because of that, the more stable radical is our tertiary radical. And so that radical will form at a much faster rate comparatively, and that tertiary radical is actually going to give us overall not the radical, but instead as our major product, that tertiary alkyl halide, right? So this guy will be the major product comparatively to this guy or this guy or this guy. So there's a lot of different options here, but again, our major product is going to give us that tertiary alkyl halide coming from that tertiary radical. Okay, so we had just covered the kind of regioselectivity of the halogenation reactions, right? So both bromination and chlorination are going to produce the more stable radical in the process. So we're going to see the production of the more substituted alkyl halide as a result. And again, bromination is much more susceptible to that. So we're going to get pretty much 100% production of, again, the more substituted brominated product, okay? All right, so now we're going to talk about a little bit different topic that we usually have to talk about when we do all these reactions, which is stereochemical outcomes, right? So it's their stereospecificity, is their stereoselectivity, etc. So for example, and I shouldn't have started with the candy before I started doing this. So anyways, let's say that we took butane, right? So we talked about propane. Now let's imagine that we're looking at butane and we're going to undergo this radical chlorination reaction, right? So again, we have two possible products that we can produce. We could get the primary alkyl halide here, or we could get, if we take one of these hydrogens from one of these interior carbons, we could get the secondary alkyl halide. So just as a note, just real quick, if we had taken either this hydrogen or this hydrogen, it's going to give us the same product regardless, right? If we had taken either this hydrogen or this hydrogen, it would have also given us the exact same product, which is this guy, okay? So now when we do this, and let's say we do this reaction and we're looking at the formation of this product, note that we took something that did not have any chirality centers in it, and by putting that chlorine at that position, we have now introduced, or I shouldn't draw anything there, we have now introduced the fact that we have introduced a chirality center into this molecule, right? So again, this carbon specifically, by putting that chlorine there, now has 4 different substituents around it. So by undergoing this reaction, we're introducing a chirality center to that molecule. So now the question is, well, is there a preference with respect to what enantiomer we're going to get, you know, with respect to absolute configuration? Are we going to get an R? Are we going to get an S? Is there a preference, right? And so the answer to that is that, again, we're going to treat these radicals as kind of like an intermediate between a carbocation and a carboanion, right? So as a reminder, a carbocation was, again, that nice little trigonal planar molecule. So let me actually make this a little bit more legible, right? So carbocation was a nice little trigonal planar molecule. Again, it's trigonal planar, so all of these bonds lie in the same plane. With respect to carbocations, we then had that pi, or that p orbital, sticking up above and below the plane of those bonds, right? And so we had talked about, okay, this carbon radical, it's very similar to a carbocation. It's also going to be considered essentially trigonal planar. Or if it is kind of trigonal pyramidal, it's a very shallow pyramid. Regardless, though, it's going to behave very much like a carbocation does in something like an SN1 reaction, right? So remember, when we would form that carbocation and we were doing, let's say, an SN1 reaction, we had our nucleophile come along, and that nucleophile had no preference from whether or not it attacked from this side or whether it attacked from this side, right? If it had attacked from, let's say, the top, that would have given us one configuration. If it instead had attacked from behind, that would have given us a separate configuration, right? And again, it had no preference which way it went about doing that, so both ways essentially had like a 50-50 probability, okay? So that's exactly what's going to happen in terms of our radical bromination reaction. That radical that forms as an intermediate, we're going to treat like a trigonal planar species, and now it's going to go and attack that halogen, right, via our radical reaction, but it doesn't have a preference from whether or not it attacks from, let's say, this side or whether it attacks from this side, right? It's essentially going to be 50-50 either side depending on whatever the reaction is, okay? So as a result of that, long term, what we're going to find with these bromination reactions, these radical bromination or halogenation reactions, is the production of a racemic mixture, right? So if we have a molecule that has no chirality centers in it, and we undergo this radical halogenation, we're going to get, and by doing so, we get a new chirality center introduced. The product of that is going to be 50% R, 50% S enantiomer. So it's going to be a racemic mixture, okay? That's a lot to say, mainly just that there is no stereoselectivity, there's no stereospecificity. We only get, if we are introducing a chirality center, we're going to make a racemic mix. So that is no chirality centers introducing a chirality center. What happens if we do have a chirality center and we do the exact same reaction? So we undergo this radical bromination reaction. What happens to the configuration about that chirality center? Again, what we're going to find is it's going to go through a trigonal planar intermediate species, right? So it's going to go through that trigonal planar intermediate, which is that that radical carbon-based species. It's then going to react with something else, which is going to produce the final product. So the answer to this, if we had a chirality center, what happens to its configuration is we are also going to get essentially a 50-50 mixture of R and S. Oops. Right, so if there was a chirality center, bromine, no, that's that. And then we have bromine. Essentially, the product distribution is going to be 50% R and 50% S. We will also make a racemic mixture out of it. Okay, so again, if you just want the synopsis of this, we have no chirality centers, but by undergoing this reaction, we're introducing a chirality center. We're going to get a racemic mixture as a product. If we do have a chirality center, and it actually reacts in this reaction, we're also going to get a racemic mixture as a product, right? So 50% R, 50% S. Okay, so now we're going to consider reaction via these radical halogenation, or more importantly, radical bromination with things other than alkanes, with reactants other than alkanes. So thus far, we've only been dealing with alkanes and what are their regiochemical as well as stereochemical outcomes with respect to this radical bromination or radical chlorination reaction, right? So now what if instead we took an alkene and we tried to undergo this radical bromination reaction? Okay, so coming from the example problems that we just did, if we were saying, hey, I've got this reaction, I want to know what the major product is, the way to answer that would be going through and looking at the radicals or the alkyl halides that are going to be produced depending on the hydrogen that is abstracted, right? So if we took this guy and said, okay, what if we abstract, let's say, this hydrogen up here, right? So let's say that this hydrogen is there. We can abstract this one. We'll call this hydrogen 1. We also have a hydrogen here that we can abstract. We'll call this hydrogen 2. And then we'll also consider what happens if we abstracted, let's say, this hydrogen. We'll call this guy hydrogen 3, okay? So again, we're going through, we're trying to figure out the type of radical that are going to be produced depending on the hydrogen that we actually abstract, right? So for 1, if we abstract that hydrogen 1 in the first step, what we're going to produce is a radical on that carbon double bond, right? So if you guys remember back from the beginning of the chapter, this was a vanillic radical, which was super unstable and very, very, very high in energy. We could also consider what happens if we took away hydrogen 3. So if we came in and abstracted hydrogen 3, we would get the production of this radical, which is a secondary radical. We can also consider what happens for hydrogen 2. And so for hydrogen 2, if we abstracted it, we would also get the production of a radical here, which is a secondary radical. But this is also a special type of secondary radical in the fact that this is an allylic radical, right? And so allylic radicals were more stable than the tertiary radicals and the secondary radicals, etc. Because again, there is a resonance structure that we can draw for this where we have our one resonance pattern that we learned. So another resonance structure for this guy is the double bond being here and the radical being here, right? So because this is an allylic radical, it is resonance stabilized, and so because it's the more stable species, or the more stable radical that is produced, it's going to have the lowest activation energy, and this is the one that's going to essentially be formed to a much greater extent, okay? So if you took this guy, alkene, what you would find is whatever that hydrogen is in the allylic position, that's the one that's going to react, because again, this guy has the lowest bond association energy overall between all the other hydrogens. Right, so the product overall would be reaction of this guy, which would give us this as our brominated product, okay? Now, you should also see a little bit of an issue with this, right? So this is great if this was the only reaction that occurred. But the question is now, well, have you ever seen a alkene in the presence of bromine before? Like, have we ever seen a reaction where this alkene reacts with bromine? And the answer to that is yes, right? So when we went over the addition reactions, anytime we had an alkene, let me go ahead and redraw this. Anytime we had a carbon-carbon double bond, an alkene, in the presence of molecular bromine, we would undergo an addition reaction, right? That went through that bromonium intermediate, and the product that we would get would essentially be that dihalide product, right? So these guys would add in an anti-fashion, right? So they would add across the double bond on opposite sides. So we'd get one, and then the production of its enantiomer. So that's an issue, right? What if we only wanted this guy and we didn't actually want the addition product, right? If we took an alkene and we added bromine to it, then we would get that addition product as well. So to kind of prevent this and to only get our mono brominated species, instead of using Br2 as our reactant, we're instead going to utilize this thing called N-bromosuccinimide, which we abbreviate as NBS, okay? So NBS has a nice, easily cleavable nitrogen-bromine bond, right? So the first step, this is how we're going to initiate the reaction. So if we initiate, we're going to see homolytic cleavage of that nitrogen-bromine bond. That's what's going to produce our bromine radical, which is then going to move forward in the propagation steps of this mechanism, right? So instead of it being the bromine bond that is homolytically cleaved, it is instead the N-bromosuccinimide bond that is heterolytically cleaved, which is going to produce our bromine radical overall. So this N-bromosuccinimide is going to produce our bromine radical. It will not react with the alkene. So if we use NBS as opposed to Br2, the only product we are going to get is that monobrominated alkene, that allylic brominated alkene, right? So that's why we would utilize NBS in this case. So if you're dealing with alkanes and you want your brominated product, you can use Br2 in the presence of H-nu, but instead if you're dealing with alkenes and you don't want a mixture of products, you only want your one brominated product, then you should use NBS in the presence of H-nu. Okay, so that is important if we're dealing with alkenes. I should note that even though we're using NBS, we can still sometimes get a mixture of products, right? So for example, let's say that we had this alkene. We react it with NBS so that we don't get the formation of that addition dihalide product, but we still actually get a mixture of product in this reaction. So the question kind of is, well, why do we get a mixture of products here? So the answer to that comes in the fact that, well, the radical intermediate that forms is going to come about from the abstraction of this hydrogen. So when we abstract this hydrogen, what we get as a product is an allylic tertiary radical. Right, so this is the most easily cleavable hydrogen-carbon bond. This is going to be the most stable radical intermediate. So this is the thing that's going to be the fastest to form, okay? So this forms, right? And this is where we're essentially going to get the production of this guy as one of our products. But the question is, well, where does this guy come in? And the answer to that is, because this is an allylic radical, there is another resonance structure that we can draw from this. So this guy is resonance stabilized. The other resonance form, we have one electron forming a double bond here, the other coming from the pi bond, and then the other electron being left behind here. So the other way that we can draw this, or the other resonance form for this, has the radical out here as an allylic primary radical, right? So both of these guys exist because, again, it is resonance stabilized. And when it is in this form and it reacts with the bromine, we're going to get the production of this primary alkyl halide, or I guess alkene halide, instead of the tertiary alkyl halide, right? So with alkenes, especially the allylic bromination, sometimes you will still get a mixture product because of this resonance stabilization, so you have to be aware of that. Okay, so go ahead and try this guy out. I want to know what are the products obtained when we treat both of these guys with MBS in the presence of light, in the presence of H nu. So go ahead and pause this, predict the products, and then come back to find out. And I want all of the products. I guess I should note that, not just the major product. Okay, so again, we know that we're going to undergo this radical bromination. Specifically, we're using MBS, so we know we're not going to get any addition products, right? This is what we're going to always use when we have a double bond. We can also use MBS with just alkanes too, I should note that, but just, yeah. Right now, we have to use MBS if you only want the radical brominated product as opposed to the added product with respect to these alkene reactions, okay? So, again, we're looking for the most easily cleavable carbon-hydrogen bond, or the hydrogen bond that, if it's abstracted, is going to give us the most stable radical, right? And so because we have this double bond, we know that we do have an allylic position to that double bond, and those hydrogens in those allylic positions are probably going to be the hydrogens with the lowest bond dissociation energy. They're going to be the hydrogens that are going to produce the most stable radical, right? So if I had taken this guy, or if I had taken this guy, doesn't matter, I'm going to get the same thing overall. So this guy is going to be the initial product overall after the first propagation step, after that hydrogen abstraction step. If this guy gets attacked via bromine, then we're going to get as a product, actually, hold on, I want to copy paste this again. Yeah, maybe one more time. Okay, so if this guy gets formed, then as a product, we're going to get bromine here. But just as a note, again, there are resonance forms for this one. So this is not going to be just one product form because we'd have to deal with these resonance forms. Instead, we can draw a resonance structure for this using our single-headed arrows. That's super ugly. But essentially that guy, the resonance structure will look something like this. Or we have a double bond here, and the radical is out here. If this guy gets formed, which it will get formed, then instead of this being the product, then we are going to get, let me erase this guy, the production of this guy. So here, if you wanted the correct answer, you would predict both of these products, right? You would predict the production of this one but because of resonance, you would also predict the production of this one. Okay, so same thing down here. We've got an alkene undergoing this radical bromination. Again, I think we've already looked at this one. I think we just did this for the most part. This guy, we have a hydrogen here that would produce a tertiary radical as well as an allylic radical. Right, so this is going to be the most stable. If we get reaction here, then the overall product is going to be the bromine there. But again, like I just stated, for the top one, this does have a resonance form, or it does have a resonance structure that we can also draw that would put that radical out at the primary position. If this guy reacts, then we're going to get this as a product. So because of resonance, we will get both of these products overall. So we will get both this guy and we will get this guy. And you should be able to predict both of those. Okay, so that's all I have for now. I may come back to one last mechanism or one last reaction, depending on how I feel about it. But I'm going to go ahead and upload this, and then I'll upload the homework for Chapter 10 as well, so you guys can get started on that.